Concave lenses by Gerald and Darius. What is a concave lens? In a concave lens, the edges curve towards the observer. In our problem, we'll be working with a concave lens. In this diagram, this is how we will solve a concave mirror ray diagram. So first, we're going to start with a visual example, and what we're going to do is we're going to go parallel to our principal axis and reflect through the focal point. Then we're going to go reflect through the focal point, which is indicated by the F, and then we're going to go parallel to that. Where we circle here will be where we create an image. This dotted line is your image, and where the circle is where the rays intersect. These are the rules of a ray diagram. First, a ray diagram, you have to go parallel to the principal axis and reflect through the focal point. Second, ray is you go through the focal point and then reflect back towards the principal axis. Remember the ray diagram? The area that was circled is the point where the two rays intersect. This is where the image is located. So again, we're going to go parallel to our principal axis. Then we're going to reflect through our focal point. Then we're going to reflect through our focal point and go parallel to our principal axis. Circled here is your image. The variables that we need to know: focal length and radius of curvature. The focal length is indicated by an F, and the radius of curvature is indicated by the C. Real versus virtual. A real image is located in front of the lens, and a virtual image is located behind the lens. We use a dashed line. Upright versus inverted. An image is located above the principal axis. That makes it upright. When the image is located below the principal axis, that makes it inverted. We indicate this by an image being pointed up for upright and down for inverted. Here's a couple of equations that we need to know. We need to know that 1DO plus 1DI equals 1 over F, the fundamental lens equation. And then we need to know that magnification is equal to negative DI over DO. That's the magnification equation. More variables. The object distance is measured by DO, which is in centimeters in this case. And DI is the object distance, which is measured also by cm. And then the magnification is also in centimeters today. Solving the problem. First thing we want to do is write our givens. Our focal length is 5 centimeters and our object distance is 15 centimeters. We're going to use our fundamental lens equation. So we're going to plug it in, and it's going to be 1 over 13 plus 1 over di, which equals 1 over 5. And we plug the numbers in. Okay, important. We use the first to find the object distance. We require this information in order to find our magnification. Okay, after plugging in the givens, you must then subtract the 1/3 from both sides. That's as we see right here. We did 1/3 subtracted on both sides, and this is what we have our distance object to be equal to 8 over 65. And then we leave it as 8 over 65 and we treat it as a division problem. So now the remaining 8 over 65 equals 0.123. This is our distance object. So switch your DI with 0.123 and divide it again. So equals 1 over 0.123, which equals 8.13 centimeters. This is the image distance. Okay, now that we have the image distance, we can plug it in and find our givens to find our magnification. Using the equation, m equals negative di over do. Plug it in, plug it in. So we're going to take the negative the 8.3, and we're going to do negative 8.3 over 13 to find our magnification. And this is seen once we wrote our givens down. Okay, once we plug that in and we properly divide, we get the magnification is 0.265. Presto. Okay, now let's draw our array diagram like we discussed earlier. Alright, so basically what we're going to do from our object is we're going to go parallel from the principal axis and go reflect through the focal point. Then we're going to go through the focal point and parallel from the principal axis. Where I circled here is our image. Okay, so let's label what our picture is. Our picture would be considered to be a real image because it's in front of our lens. Then also our picture would be considered to be inverted because it's upside down and not upright. Remember, upright, inverted. Okay, and then also our picture will be enlarged based on the fact that this arrow is bigger than our object. Our object is smaller than our image, making it an enlarged image. So this is what we got. We got a real, inverted, and enlarged image. Don't forget, real means it's in front of the lens. Inverted means that it's upside down, and enlarged means that the image was bigger than the object. Now, this is concluding our tutorial on concave lenses. Please don't forget, if you need any additional help, please see Ms. Deverona. Thank you.